Welcome back to the final revision presentation of the quadratic function. Here it is, part 4, and in further presentations we're going to learn the next level, and it's actually a bit easier than doing some of the algebra that we've got here. But this one is called solving quadratic equations, and you've done a bit of this. And why do we solve equations like this when we put the quadratic equal to naught? Well, that's of course where the graph cuts the x-axis. Okay, when the function is equal to naught. So we're trying to find these points here. Look around the screen though. We want to move into the area where quadratic functions can be used to mean something in a practical sense. Like, what about this box up here? What about the surface area of a box? Would we be able to find the maximum surface area? Or that might give rise to an equation. When is the surface area equal to 100 square centimetres or something? And you might get an equation out of that. And down here, what are these dudes doing? Clothing people, leather jacket company, and here might be their mathematical model for how many dollars revenue they get if they make X jackets in there. So this could be a practical problem. And they might want to know, well, how many jackets do we have to make $3,000? And then you would be having an equation, move it around, probably to move terms so that you get a 0 on the right, because we know that if you've got a 0 on the right, you can factorise the left-hand side. Then you can say product is 0 when one of these terms is 0, when they're null, the null factor law. Remember all that? So it's going to be interesting seeing how we can apply this. What about this one over here? Might have seen that before, where you've got maybe the maximum area enclosed by a pen there against the brick wall. That might give rise to a quadratic. And we'd be interested in finding things about those. So let's go back and just check up solving quadratic equations. So come down and let's review the things we're supposed to know already. Here they are here. Quadratic equation, the roots or the solutions of an equation are the values which make it true. So you're trying to find the x value to put in there and there so that it comes to 0, or where its graph cuts the x-axis. Okay, what are the steps? Make one side of the equation 0 by transferring all terms, transposing terms to all one side. Then if we factorise the left, you can use the null factor law like I was speaking about before. If you factorise the left like this, then a product of factors is 0 if one of the factors is null, itself 0. So either this one or this one has to be 0 to satisfy that. And then you solve those equations. Alright, let's practice it. You're supposed to know this. I hope it is revision. Let's have a go at these now. 3x squared plus 5x equals 0. All terms on the left and 0 on the right, that's good. Now here's a common factor. There's x's in both, so take out a common factor. What do you multiply x by to get 3x squared? It's 3x. What do you multiply x by to get 5x? It's 5. So now we have a product. So product is 0 when either x is 0 or 3x plus 5 is 0. So that's a solution. And then solving this one, subtracting 5 from both sides and dividing by 3. Reversing the steps. Okay, so we have our two solutions. This one looks a little bit different. Remember how important the null factor law is? So that means you have to get a product equal to 0. So get 0 on the right by subtracting 5x and subtracting 6 from both sides. Then we can factorise it. X takes 6 by x plus 1 is 0. Therefore either x takes 6 is 0 or x plus 1 is 0. So x is 6 or x is neg 1. Got the idea? Okay, let's go back and try and practice that stuff. Here's first set of problems and their solutions there. So try to copy what we've just done, common factor or a product of factors, and go through each one with one of those types. And you probably need to do all parts here to get the skills up again, all parts. And then check your solutions down here. Alright, let's go on. There's a few more types that we did last year. Here's the next type. What we've got is there's a 4x on the right, so we don't want that. We want to subtract 4x down here so it equals 0. So that when we factorise this like that, one of the factors is 0. Well, they're both the same here, 2x take 1. I don't know, did you see that? This is a square, this is a square, and this is twice the product, going straight to a perfect square. Or you could go through FOIL, reverse of FOIL, try factors here, and then 1 and 1, both negative, and do it that way, if you can't spot a perfect square. What about this one up here, a harder type? Take 11x from both sides, take 10 from both sides, and now you want factors of 6, 2x, or 2 and 3 to give 6x squared, factors of 10, 5 and 2, and using a factorisation technique, either the cross method, or splitting the x term, or trial and error. So then the answer to this, what makes a product 0? Either this factor is 0, like this, so 2x equals 5, x is 5 over 2, or this factor is 0, 3x plus 2 is 0, 3x is neg 2, x is neg 2 over 3. So they are our two answers. Alright, so they are harder ones, a little harder. So come down and try and do the same thing. You'll be glad to know we're going to do this in an easier way later on. We won't be doing all the factorising. Okay, so basically you're trying to do this to each one. So you get 0 on the right, and then try to write the left as a product of factors, then put them equal to 0. Okay, I think here you might just try every other part, or what's called alternate parts. So that's A, C, E, etc. Alright, let's look at the answers to those then. Here we are. They don't show you the factors, so you have to work backwards from that, and I suppose you could, think, well, how would I get answers of neg 2/3 and 6? What would the factors have been? Would have been what? 3x plus 2, working backwards, and x takes 6, wouldn't it? You could work backwards to check your work there, so that you're looking to see when this is 0 or when this is 0, get those two numbers. So play around, check your answers, see if you can work out the factors. Alright, let's go on. Some slight variations now. Here's one here. Oh, there's no x squared. But if you want to solve for x, you want it out of the denominator. So here we are. Multiply both sides by x to get rid of that fraction. So here it is here. Multiplying by x on both sides. This becomes, oh, there it is. There's x squared, and then when you're multiplying here by x, you get just 2. And then adding 7x to both sides. All terms on the left, 0 on the right, and then we need to do the factorising. Okay, so then the answers are, one of these factors must be null. If that is 0, x is neg 2. If this is 0, 3x would have to equal neg 1. X would be neg 1/3. So over there. All right. Have a go at some of these coming up now. Here we go. Question 3. So you need to expand all of this and then move the terms across, that sort of thing. So a bit of work to do and simplify. I think because these are all different, I think it would be good to do all parts here. Okay, and there's only half a dozen. And then check your answers. Where are they? Oh, here they are, coming up below here. There are the answers to that little group there. All right, are you getting powerful? I hope so. Got a little bit more to do. Let's have a look at this one. Why is this one special? Well, you can see it's cutting the x-axis, the graph, and so this should have 2 roots or 2 solutions. Okay, but the problem is, can you see it? It is not factorisable. Do you remember what you did last year with this? Okay, well, it was the subject of the last presentation. We complete the square. So watch me do it now. x squared plus 4x. Now, my wish number to make a square, half the 4 is 2, square it and add it on. So that will give me a square, that process. Bring the 1 down and also take off the 4, or put it on the other side, add 4 to both sides if you like, please yourself. So this is x plus 2 all squared, take 3 equals 0. Now get the square by itself, x plus 2 squared equals 3, adding it to both sides, so that implies that, that implies that. And therefore now, taking the root of both sides, remembering they're two numbers squared to give x plus 2, it'll be a positive or a negative, because a negative times a negative is also positive. So x plus 2 could be either of those two, root 3 or neg root 3. Okay, so x therefore is neg 2, subtract it from both sides, plus root 3, or neg 2 take root 3. That's how we would generally write it. Or root 3 take 2 and neg root 3 take 2. That would do as well. So this is a very important process because we can't factorise it. There's no other way of solving it apart from completing the square. So these steps here, linking to the last presentation, are important. You can see, I think, from the answers here why you can't factorise. These intercepts over here, come over here now, are not fractions or whole numbers. They're square roots. And you'd never be able to spot those and factorise. Remember, we want factors of this number to give our 4 in the middle. And quite clearly, there aren't any easy fractions or whole numbers involved here. So these are called irrational zeros or roots. Irrational roots. They involve the square root sign. They're irrational. Can't be written as a terminating decimal or a recurring decimal. Only one accurate way of representing an irrational number, and that's with that root sign in these cases here. All right. Okay, let's go and do that completion of the square idea. So I want you to try and do the same thing. Oh, well, they've done it here. Okay, you've only got the last little step to do. Find the square root of both sides. You don't actually have to create the square, so that's a bonus. So you might try all parts here again, because you may have forgotten that this is a way in the previous work that we did solve an equation by using a square. Okay, let's check the answers. Yep, look at them. They've all got these surds in, square roots. Okay, and that's why we need to complete the square. It's not possible to factorise these. Okay, there's one more type, I think, still to go. Let's have a look. Here it is here. Oh, that's the one I've just done. Okay, so we are doing what I just did there. Remember, well, they put the one on the other side, and then half the number in front of x is 2. Square it and add it on is a perfect square. And square it to the other side as well, add it to the other side. So slightly different setting out. Will be the same answer. Okay, and here's the crucial step. The wish number to make a perfect square is half the coefficient of x, squared it and add it on. I think you need to do all parts here to get that skill level up. This is a very important notion, and it helps us go on with further work later. So let's have a look at the answers to those. Yep, there they are there. Again, characteristic of this type of problem where it's not factorisable is the square root coming from completion of the square. Well, a little bit more to go, and then we will leave it. And here they are here. Of course, you might have expected these. Completion of the square, where the number in front of x squared is not unity, is not 1. So the secret thing here is to divide through by 2. Okay, the coefficient of x squared. So we come down to here, and then you can put that on the other side. Just leave it there. Half the coefficient of x, square it and add it on. Square it and add it on to the other side as well. So we get our square, working with fractions, Here's a secret. 1 is in fourths. Make the others fourths as well. So you get 6 away from 25 is 19 fourths. And you can take the square root. Remember, plus or minus the square root. Root 19 on 2. And take away 5 over 2. So 2 answers there. Neg 5 over 2 plus root 19 on 2. And neg 5 over 2 take root 19 on 2. So don't forget, you must divide by the number in front of x, or the coefficient of x, first of all, to reduce it back to the standard completion of the square type. Right, again, I think you should probably try all parts here, get the skill up. Let's have a look at the answers and come down here, and then I'm going to say cheers for now. And I'm going to catch you in the first presentation of the new work, and I think it's easier. So that's something to look forward to. See you then.